Alright.
Cool. Looks good.
Good.
So we're the Formula Electric team, team 3 I believe for the E section and team 21 for the ME section. I'm George Nimick.
Sam Risberg, Scott Dell,
Danny Covio.
Tomas Washington.
Steve Vincent.
And we're going to kind of start over with a brief overview. As you guys know, we're an electric car, but we're going to have, and we're going to be in the electric category, of course, but we're going to have both components, both mechanical and electrical, and that's why we have both types of students here. And so when looking at the car, what we're proposing you today is a design which you guys, or we're hoping that you guys will take a look at our budget and kind of accept it and help us with it. But basically our direction towards everything was in terms of what we see feasible, what we feel is tangible, what we feel we can actually build, and then what we propose that budget to be. And that budget will be something that isn't going to be a top of the line car, but something that we feel will help us perform very well in the competition, compared to teams such as the Italian team that have $250,000 bar or something like that. Something that's very competitive but very reasonable comparatively.
What's your name again?
George Nimick.
George.
And so of course some of the constraints that we have to look at are going to be what we feel you guys might be able to give us in terms of budget, and then the rules of course constrict us in certain ways and that we have to abide by them. And just kind of as an example, for budget, yes, it's very possible to reuse some parts that are already on the hybrid vehicle that exists now. This is University of Texas at Arlington, and this is nearly every vehicle they have from 1984 to 2008. And as you can see, there is a distinct progression that happens from year to year. Towards the newer years, there's some slight ones, but it kind of shows you how the old teams like this that are able to keep vehicles that are already existing, they can use that and expand upon it instead of having to start over from year to year. And this is why we would like to propose a budget that will allow us to purchase new parts and be able to keep the existing vehicle to kind of show a progression of our school and to be able to better represent our school.
A quick question, wasn't there some rule though that you had to change the body design because of the...
Every 2 years.
Yes.
Right.
We're talking about internal.
So we're going to be building a new car, but
I got you.
if we don't have enough budget, we may have to take components
Reuse
off of it,
parts. Okay.
right? Which kind of leaves an empty frame that nobody will be able to reference from.
Gotcha.
And so basically this is going to be how our project is broken down. For the mechanical section, we're going to have chassis, braking, steering suspension, and then the finite element analysis, which goes along with the chassis and possibly other components in the braking and suspension and steering. And myself and Sam will be doing chassis. Tomas and Steven will be working on suspension and steering, and then Tomas and I will also be working on the finite element analysis, since we're both in the finite element method class. In terms of the electrical system, Scott here is in charge of that, and he's going to be working on battery management and the accumulator section, and Danny Covio will be working on the motor design / propulsion. And this will kind of bring us over to
Go ahead and take over. Again, my name is Danny Covio, and I'm first going to take a look at the top level design. This is, I don't know if you can see all this, but everything that's in yellow is some type of sensor. The orange is a low voltage accumulator, like this type of color. And anything with an arrow that's this type of orange is a low voltage power line. And the high voltage accumulator is up there in red. The dark red lines show the high voltage lines, and it also points in the direction of current flow. And some of these you'll notice that it's pointing here and pointing there. It just means that there will be a line going each way, a hot line and a ground line. And then we have like charging devices, the charger up there, which charges both the high voltage battery pack and the low voltage battery pack. Signal lines are the dashed. Anything that's like a logic device, the electronic control unit, and we actually have 2 controllers, and I'll talk more about that. And we have a whole bunch of array of sensors and some necessary components to operate the controllers properly. I can take a moment here if you have any questions or if you'd like me to explain it further.
Just a quick note, just for future reference, when you're doing the power connections,
Yes.
I don't think it's necessary to do the bidirectional areas because
Okay.
everyone knows there's a return current. So show
Okay.
the direction of power flow.
Okay.
So power
Okay.
flowing from the supply to the device.
Well, I wanted to keep it to one line either way.
Right.
But,
Yeah,
okay,
but just
I'll do that.
a single head on the arrow that would make it clear which direction the power is.
And one thing is you'll notice that there are 4 motors, and that's 1 on each wheel, and again, I'll explain more about that as well. Any questions right now? Okay, propulsion and motor design. So as I was saying before, and as you saw in the diagram, we're actually proposing 4 electric motors, 1 on each wheel. And for simplicity, especially since there's only 2 electrical engineers on the project, we'd like it to be all the same type of motor. We currently have actually what's an Agni 95R motor, and it's an excellent motor. And so we're proposing right now probably 3 more of those, but we also are looking into other motor choices. Now these motors will actually be mounted on board the vehicle per the recommendation of the MEs, because we're trying to keep the unsprung mass as low as possible. And one of the key concepts here is that we have 2 motor controllers and 2 motors per controller. So in other words, you're going to take these 2 motors, wire them in series because they're permanent magnet DC motors, and double the voltage of your controller. And what that'll do is, in a sense, create somewhat of a electronic differential effect when you corner. So in a sense that could be bad. Like if a wheel lifts off the ground, all the power will be transferred to that because it'll spin and have the most resistance. So you'll have the same current traveling through both motors, but you'll receive more power over there, but it also protects the system from harm and allows us to corner very easily. And there will be 2 high voltage battery packs, but they will actually be linked from front to back. It's just basically 1 in the front, 1 in the back to help balance the weight of the car. Good question is why all-wheel drive? First thing you could think of is traction at all 4 wheels. So you have something propelling all 4 wheels and cornering stability with that whole differential effect. And then we have something called load transfer. And during deceleration, the load of the car is actually transferred more to the front wheels. So you can use the regeneration of the front wheel motors to actually capture as much electricity back into the battery system as possible. And we will still have regenerative braking on the rear wheels, but the front wheels will be far more effective than that, as well as acceleration. Now, this will be an all-wheel drive system, but it would still be biased towards the rear wheels because when you accelerate, you're getting more force on the rear wheels, so you'll get better traction back there. But over here, actually, this was something I found on motortrend.com, and it compares 3 different cars that have very similar amounts of power. The engines are all located in the front, and you have a rear-wheel drive, a front-wheel drive, and an all-wheel drive car. And the key thing that I want to point out here is the acceleration from 0 to 30 miles per hour. With the rear-wheel drive car, it was 2.1 seconds. Front-wheel drive was 2.4 seconds, but the all-wheel drive was 1.2 seconds, considerably less. And one of the key things about this competition, the Formula SA dynamic events, is that during the autocross and endurance events, we're only going between about 25 and 35 miles per hour average, and there's a lot of turns and U-turns and slaloms and things like that, so there's a lot of acceleration, deceleration. So that 0 to 30 mile per hour acceleration should really be able to benefit us in actually outperforming other teams. And the electric drive, this is just a short breakdown of the motors themselves. They cost about $1,600 a piece, and we still need 3 of them. And so this is our estimation of almost $5,000 for the motors. And basically they must work in such a way that they safely, efficiently, and quickly propel the vehicle. And they should all, as I said before, they should be the same make and model to simplify the design. And this is the Agni motor that I mentioned before. We already have 1 of these. Some of the really nice things is the 93% peak efficiency. The red line here is the efficiency versus amps. This is amps down here. and it hits about 80% at that's 50 amps, and puts out 30 peak horsepower. It only weighs 24 pounds, which compared to many other motors, they weigh 35 pounds and up for similar performance, yet their efficiency was usually less. Has a 400 amp peak, 72 volts DC, so our motor controller system only needs to be 144 volts, which is very common. And it also revs up to 6,000 RPMs, which is great for allowing us a lot of torque, a large torque band. Motor controllers.
Why you say you need 144?
144 volts DC.
Why if the motor is at 72?
Because the two motors will be wired in a series configuration, so that, okay. So basically, a single motor controller should be able to control either the two front wheels or the two rear wheels simultaneously. It should also have regenerative braking built in, and should be specifically built for the type of motor. So if we have a series wound motor, it should be a series wound motor controller. And it needs to be able to handle at least twice the rated voltage of the motor and the same maximum current. And I priced those at about $1,300 a piece, and with shipping it totals about $2,660. Okay. The motor control system will consist of two permanent magnet motor controllers. One will control the front motors, both front drive wheels, and due to this system, what Scott and I have been discussing so far is that the front motors will actually not be on or actually propelling the vehicle most of the time. It will mostly be the rear wheels, just so that we have less systems operating. And to simplify some things, so that we only have power going to the rear wheels where we actually should have better traction. But anytime we decelerate, that would be more focused towards the front wheels.
Well, then don't you lose that advantage from that comparison where the four-wheel drive had a faster acceleration?
Well, they wouldn't be engaged like if you're just coasting along or something like that, but during hard acceleration or cornering where slip is detected, because actually from the top level diagram, I didn't mention it, but we will have some type of encoder on each motor to detect the RPM count, and then compare that with all of the other sensors, and if one is slipping, then it will transfer power to another wheel. And the separate battery packs in front and back to help with the weight balance. Throttle control. Basically, we'll have a single accelerator, or called the potentiometer box, that'll look something like this. And it'll be mounted just like your regular car would be. Gas and brake, one-speed transmission, no shifting or anything like that. And anyway, the theory behind this is that you'll press the accelerator pedal, and that will send a signal to our electronic control unit, which will be some type of microprocessor, possibly an Arduino or Palalu, something like that. And that will then take that along with other sensors, sensor data like the RPMs, the brake pedal, and we'll plug that into an algorithm that'll determine what amount of torque to send to both the front motor controller and the rear motor controller. And then the motor controllers will determine how much torque. Excuse me. Yeah.
I'm Scott Hill, and I'm going to cover the battery management and accumulator system on the vehicle. The type of accumulator that we're leaning more towards right now is a lithium-ion type battery. It's a polymer battery, and the nominal voltage for these batteries is about 3.7 volts. And with the configuration that Danny was talking about with the motor controller, since we're going to need about 144 volts, we've decided to go with a 3S battery pack, which means that the battery pack will have about 11.1 volts per pack. And the math works out almost perfectly to where it's about 13 batteries in series to achieve the 144 volts. And in order to achieve the proper acceleration in the competition, we've chosen a 25C battery, which can achieve up to 30C discharge, or 30C 10-second burst. And we were also limited on the configuration of the batteries by the competition rules, because they say that any parallel connections with the batteries have to be fused. So we couldn't go with any type of battery pack that has, say, like a 3S 2P configuration that would give us more capacity in the battery. So that's why we decided on just the 3S configuration. Any questions on that?
Did you look at, the series resistance of the batteries and at the current you're operating at, how much voltage drop there'd be from that?
Not yet.
Okay, it might be a good idea to look at that. I mean, if you're driving the batteries at a high current level compared to what they're normally operated at.
Yeah, and I'm gonna do a more in-depth comparison between this battery and other types in our next milestone. I just wanted to show what our current line of thinking is right now on that.
Okay.
And then here I go over a little bit more of the battery characteristics. As per the rules, we cannot exceed 5,400 watt hours of capacity in the accumulator. And at 144 volts, that's going to be about 37.5 watt hour or amp hours. But that's not accounting for efficiency in there, which they do talk about in the rules as well. So we're going to aim for 40 amp hours as our capacity of the battery system, which should be well underneath the limit once the efficiency has been calculated down there. A couple different configurations we looked at as far as the capacity of the batteries. We looked at a 5 amp hour battery pack, and we looked at a 5.8 amp hour battery pack. The advantage of using the 5.8 versus the 5 amp hour is we could use one less parallel string, but the batteries do cost more. With the 5 amp hour, it would require 8 parallel strings, and with the 5.8, it would only require 7. But as you see here, when we compare the cost of the two, it's about $400 more expensive to go with the 5.8. So that's why we're leaning more towards the 5 amp hour at this current time. Any questions about the configuration there?
Well, one quick question. The capacity of the battery, so you're going to target the capacity as being 40 amp hours.
Yes, sir.
But, you know, keep in mind that you may not be able to run the battery all the way through its capacity because its voltage is going to be dropping somewhat as, you know, as you discharge it.
And on the next slide here that I'll show you, I did a very basic simulation using MATLAB.
Okay.
This has all 104 battery packs in there that would be used for the configuration. This here is a 13S 8P configuration, but since each pack is actually a 3S battery, it's more like a 39S 8P configuration. And this battery model that's on here was one that was built into MATLAB, and it actually has a characteristic for the lithium-ion type battery,
Okay.
so it does conform to its discharge curve.
Okay.
And on this next slide here, it was connected to a 5 ohm resistive load, but its state of charge was not taken into account with this. So there will be some control in there to make sure that the batteries don't drop below a certain voltage, which in this case it would be 104 volts. The battery pack as a whole cannot drop beneath that, or permanent damage will be caused to the batteries. So as you can see here, the areas that I circled, those are the areas that we're aiming to operate the battery packs at. Any questions on the simulation or the results from it?
So the model that you use in MATLAB is valid for this batteries, or you just use a generic model for lithium-ion batteries?
It's a generic model for the lithium-ion. So like I said, it's just a general, really simple simulation. I'm going to do some more in-depth simulations for the next milestone. I just wanted to see how the discharge curve would look with a generic lithium-ion battery. But the voltage on it is set at 11.1 volts, and the capacity is set at 5 amp hours for each battery. And then I wanted to talk a little bit about capacitors, since we're considering using them in the vehicle in order to take advantage of the regenerative braking, since they can be charged much faster than batteries can. This is still in the preliminary stages of research, so I don't really have too much to talk about it right now. But in the contest rules, they do say that on the endurance race, where available, the course will actually be optimized for regenerative braking. So that's one reason why we want to try to include that in the vehicle. And then I wanted to talk about the battery management system of the vehicle. Since they are lithium-ion batteries, they have to be balanced, or one voltage may drop too low and cause permanent damage to it. Last year's team used an e-lithium battery management system. Since we want 2 battery packs in the car, we would like to have 2 battery management systems. But we already have one of the battery management masters from last year's car, so that can reduce some cost there. And each battery pack has to have a cell board on it, which communicates with the balancer, and that needs a little bit further research, because the way that they did it on the 2019, if we did it the same way this year, it would be far too large, since we have so many more batteries. Because they used 5S battery packs, and so they had to have 5 of these cells per battery. But they do make custom ones, and so I need to contact the company and see what their pricing on that kind of thing is. So again, more of that will be discussed in the next milestone. Or I can keep any of you up to date on what I receive if you're interested in that. As far as the battery charging system of the vehicle goes, since we want to use a 144 volt configuration, we found this battery charger here on cloudelectronic.com, and it's rated to be a 144 volt, 15 amp charger, but it can be adjusted. There's different settings that it has other than just 144 volt. So if we are testing a smaller amount of batteries at some point to see how their characteristics work, we still have the ability to do that without having a different kind of charger. And then here on the next slide, I want to talk about the accumulator enclosure. Much like last year's team, we like to use the polycarbonate accumulator box for the reasons of that it's a good insulator, and the competition rules also state that it must be easily accessible for viewing at the competition. And when we build it out of a material like this, you can see it from all sides, so that viewing issue is not a problem. And we'll also use some fan cooling in the box in order to keep the batteries at a good temperature so that they don't overheat. And then I want to talk about the overall accumulator system budget. As you can see, the largest cost comes from the batteries. There may be some kind of volume discount we can get from the companies, but this is what we got off of Hobby King's retail website. So I still need to contact them. We're probably going to order a small number of the batteries at first initially to start testing them and to do an abuse test on the batteries to make sure that they can withstand the current discharge that we want to use on them. So that will be ordered sometime in the near future. And then I still need to contact eLithium to figure out about the cell boards, because I don't know quite how many of those we'll need depending on how we want to wire those up. So again, that still needs a little bit more research on it.
Question, you
Yes,
mentioned
sir.
Hobby King. How much did you sort of shop around to different sources?
I searched probably 3 or 4 different websites, and some of them were much more expensive.
Right.
This is probably one of the better prices I could find on them, but I'm still going to do a little bit more research. I'm kind of every day checking a couple websites,
Okay.
just to see if I can find any better pricing, since it is such a large expense on the vehicle.
Right. Yeah, I just want to make sure you didn't just find the first website you found that had these things.
I spent at least a couple of weeks looking at batteries.
Okay, good.
And then this here is a kind of the basic timeline for the accumulator system. As you can see here, I want to start off by getting some batteries in and start testing them. Also start designing the battery management system and doing more research on that to make sure that what we want to do is feasible before we order too much. And I also want to start, as you can see here at the tentative schedule, it starts once we get everything put together, start testing components as a whole, and then wiring in with the system and testing the system as a whole. And then that is it for my presentation. Thank you.
Okay. Again, I'm George Nemec, and I'm just going to be introducing the mechanical top-level design and some of the systems that it involves. We're going to be starting off the overview, and I tried to kind of lay this out in terms of where they're going to be positioned in the vehicle. And these are just the major components. Of course, there's going to be smaller components such as fasteners and bearings, things of that nature. But these are the main components, and basically most of these lines are going to represent linkages, like these are for the A-arms, your axles, and then this dash line here is going to be the brake lines. Basically, we're going to start off with the brake system here, and of course that involves a brake control, so that'll be the pedal, and that we have fluid, and the fluid's going to be back and forth depending on when the pedal is depressed. When it's depressed, of course, the fluid's going to flow and push the pistons for the brake calipers, and of course allow the vehicle to stop. And then throttle control, that's more electric, but we still need to design a pedal for it, or some sort of pedal, if we're not using an already purchased system from the electrical side. For the motor, there's going to be a gearbox about 1:6 ratio, and we're going to choose that over a chain just for compact safe space, basically. And then we're going to have steering system here, and then of course all the components inside of the wheels, which is going to involve the knuckle, the hub, wheel itself, and then the brake components for caliper and rotor. And so going into more depth, we're going to start off with the chassis. And as with any system, when we start off with when we design a system, we need to look at its purpose. So the purpose of the chassis basically is to provide a structural enclosure for the driver. Of course, it has to be strong, lightweight. Those are two major goals. But it also has to be preferably compact, but comfortable enough for the driver to sit in. And then you have to think about also where components are going to be mounting, and is it going to be easy to adapt, say, the suspension system to it, or is it going to be easy to do maintenance work on it? Is it going to be a hassle to take out the motors, things of that nature? So we're going to be designing around that, and then once we have a preliminary model, which we're finishing up at the moment, we're going to perform a finite element analysis and hopefully find out where the concentrated stresses are, so that we can either add more tubing members, or we can subtract members and kind of optimize the weight and the shape of it and go from there. And Sam's going to talk about a little bit more of the components that we're designing around for and how they're going to be looked at so that we can optimize this design.
Sam Risberg. Like Alex said, we're going to do a finite element analysis on the chassis, and this is an example of a formula car, or well, SAE formula car. So obviously no electric motors, it just has an internal combustion engine, probably 600cc or something. And if we do this finite element analysis, we might need to add or take away members, but as you see, we have many things to mount for. Brakes obviously are going to be part of the hub, suspension. We have to worry about where we're going to mount our shocks, and if it's going to be a tertiary link or just straight, maybe double A-arm or McPherson, where we're going to put the motors. So in this case, our electric motor would be right here, and in our specific case, we would have two electric motors, possibly on a differential or just one per wheel. You can't see too much, but this is where the driver would sit. We're going to have a lot of driver accommodations. We're going to have to make sure everybody's knees fit in, and obviously, as you can see, we have 3 members that are over 6 feet tall, so we're going to have a lot of accommodations that we're going to have to consider. Safety equipment, there is supposed to be a fire extinguisher mounted around here. There's multiple safety off switches because of the electric components and the high voltages. The steering, which obviously needs to be removed. Body panels, which you can only see about one right here, but normally you would cover the front attenuator and the impacts. And obviously the batteries, which are going to cover the entire side of our car and or back. So our budget right now, we're looking at the sheet metal, which you can see in the last picture, which was behind the driver's seat. Structural tubing, obviously, for the frame members, the roll hoop, the side impact hoop. Conduit piping, which we're planning on making a mock chassis, so we can obviously all sit in it. We have a motor to compare to, like mock mounted up, see how much room we have and what we have to work with, and that's going to be another $300. and the honeycomb aluminum impact attenuator, which is going to be around $500. So total, the chassis alone is going to be around $3,100.
Well, what's your name again? I lost track.
Sam Risberg.
Sam.
Yeah. So our timeline for this, which we are around here right now, we've already done most of our research and not all our feasibility tests, but we know what members we're going to use. We know what, for the most part, the thicknesses on the tubes we're going to use. And we've gone through a lot of the rules already, but we need to go through the ergonomics and the filament, obviously, because we have many things that you can't just find out on paper. We need physical models. After that, we're going to have an FEA analysis and conduit piping. We'll finalize our model, and hopefully by the beginning of next year, we will have a built chassis by February.
Sorry to juggle back and forth. The reason why we split the chassis is because we're both going to be working on it, and so we just want to both localize that. But actually, Steven and Tomas are going to be working on steering, which is kind of even out of the talking. I'm going to be speaking about the steering here for a moment. And the reason why they're going to be doing steering is more because suspension and steering kind of go hand in hand. Only because when you're designing the steering, not only do you have the constraints of the rule book, but you're also going to the tie rods must act with the steering, otherwise you'll get binding. So some of the things that we have to look at is, again, the purpose of the steering, and it's going to be to control the vehicle. And not only does that mean avoid obstacles, but it will mean to maneuver and whatnot. So we're looking at this, and we're looking at the possible steering options that are available, and what's going to fit our budget, and what's going to be the most feasible. So looking at several different ones, such as the rack and pinion recirculating ball, worm sector, articulated steering, and four-wheel steering. Basically, these are all either front-end ones. Of course, you've seen some which are on, say, construction vehicles, where the actual body will pivot in half to help the steering, or you have four-wheel steering with all four wheels to steer. Some of these, such as the body helping to steer, or four-wheel steering, although they're very useful, can be very practical in this design. So we're going to stick with two-wheel steering, so that kind of narrows out our selection. And then rack and pinion is very common and very easy to get and install. So we're choosing a rack and pinion set, and because of the relative weight of the vehicle, no power assist will be needed. So that shouldn't be necessary with this vehicle. And so for the installation, again, like I said, not only do you have to look at how it plays with the other systems that go around it. I mean, you can even positioning in terms of where the front motors would be, or like I said, how it acts with the suspension system. But we have to also look at where the driver's feet will be, and will it be able to be placed so that it doesn't affect where the driver positions his foot. Simple system, but yet there's a lot of thinking that needs to be involved, because once you finally implement it, you might have to make adjustments, and we prefer to get all of these adjustments out of the way when it's a 3D model rather than an actual physical model. So looking at that, we have the timeline. It's going to be a lot shorter relative to some of the other systems, and it's going to start at a later point in some systems, just because it kind of plays off of some of the major systems. So obviously it's going to start at basically the end, or towards the major development of the chassis and suspension system. And we've already done kind of the research and selection, but we're going to kind of review that just to make sure that it fits well with those. And then we'll have a preliminary design solid model, and we're going to fit that solid model into hopefully a solid model of the actual chassis and the suspension system, so that we can actually virtually move that in the solid model to see how it reacts. And then once everything is built, we're going to fit it in the actual chassis and then test it out. And come up with a rough estimate. Some of these will actually end up used for other components, but basically we need a steering wheel, quick release to get out of the vehicle easily, because everything's going to be very compact, so you're going to want to remove the steering wheel. The rack and pinion set, U-joint, which will allow the steering shaft to bend in multiple places to accommodate our compact structure. And the rod ends for the tie rods to allow the steering to, again, move with the suspension. And the hex stock is for the quick release itself, something to engage it on. And the tubing, of course, is for the shaft and the tire bolts themselves. And that'll fix into braking with Sam once again.
So braking components obviously include the obvious rotor, caliper, pads, but in this case we need to keep safety in mind more than anything. So we're going to need a single control for all four wheels, which is pretty much on every modern day car. One master cylinder applies force to 4 hydraulic lines, which, you know, one pedal causes 4 wheels to stop. What we're going to do different is 2 independent hydraulic circuits. So in the master cylinder, we're actually going to have 2 pistons. So if one fails, or if pressure is lost in one piston, the other will take over. So you could lose pressure in the front and still have pressure in the rear, and you could safely come to a stop. Obviously, it wouldn't be used for competition, but in an emergency situation, it's a backup. The brake line durability is very important. We can't use factory rubber hoses. Most vehicles now, or most factory cars, use rubber hose just because it's cheaper. It does have a Teflon coating and can take a decent amount of abuse, but stainless steel braided lines, which is used in most performance and racing situations, is better ideal for this because we're going to be lower to the ground. We're going to have more debris hitting the lines and a lot more heat, and we don't want any expansion of our lines and any air that would come from that. So to test the brakes, pretty much we would just go to our top speed or close to, slam on the brakes, and if all 4 wheels lock up, and we've done our job. So the budget is looking like this is the brake lines, the fluid, the caliper, and rotors and pads, which we might be able to reuse our old calipers, possibly. Fluid, maybe get a discount, you know, somewhere else if we're going to get .3, .4, possibly .5, because we're going to have stainless steel lines. We can have those caustic materials or caustic fluids in the lines, and the rotors and pads, we're probably going to have to get brand new of that. Can't really use 2 years ago's. So totally, it'll be $1,300, give or take. And right now, we've pretty much already started research and selection. We know what kind of rotor, or what kind of calipers we're going to be using, so we know what kind of rotors and pads we're going to need to go with those. Measurement and dimensions, that's going to go with our chassis. We're going to have to find hard points, know where the knuckle's going to go, how the rotor's going to attach around the wheel, our clearances, and we're going to have to design that all in SolidWorks, and eventually we'll mock up the parts to either our conduit frame or hopefully our completed chassis by that time. And by December we'll source the parts, and hopefully January or so we should have them mounted up to the chassis, and obviously by March we'll have that 4-wheel lockup test ready, hopefully before that actually. Suspension.
My name is Stephen Kaminsky, and I'm going to get us started on suspension. This is just an overall diagram I found online. It tells you basically how difficult it is to actually design a working suspension. There are many possibilities for all the settings on a suspension that we would take into account. And to get an actual one that performs very well is rather difficult. So these are a few of the competition constraints for suspension. It must be fully operational suspension with shock absorbers in the front and the rear. And usable wheel travel must be at least 2 inches, either 1 inch for jounce and 1 inch for rebound, with the driver seated. And that's something that they can test, and they can actually disqualify the team if it doesn't meet those specifications. And ground clearance must be at least 1 inch of static ground clearance with the driver inside the vehicle. Wheels and tires, the minimum size of the wheels is 8 inches. Tires, we're allowed to have dry tires and wet tires. Just in case it rains, we have to swap over tires. So understanding vehicle dynamics, this is a list of many but not all of the vehicle dynamics that go into steering and suspension. We have the downforce, the roll center, weight transfer, which also goes into the movement of the center of gravity of the vehicle. You have your caster, camber, and toe angles, which are going to be pretty much how you're going to set how the car turns and handles on the road. But you also have your pitch, yaw, and heave, which deal with braking and accelerating and turning.
Excuse me 1 second. There's 5 minutes left before the end of the hour. Do either of you have to leave right away at 4? You do? Are you guys, you're getting close to the end? I think
Yeah.
there's someone who has it.
Yeah, there's not much more to it. So basically
Okay.
suspension and the last couple.
And we've been asking questions as we go along, so, but just,
So our set accuracy is going to be dependent on the parts that we're allowed to use. Basically, you have your shocks, your springs, your camber, caster, and toe adjustments, and you also can mess with the ride height and the tire pressure. And if we have time to actually have aerodynamic wings on front, that'll reduce the drag over on the open wheel wheels. So independent suspension is what we're aiming to use on the front and rear. They offer better ride quality, improved handling in the turns, and you can make them fully adjustable, where you can actually adjust the toe, caster, and camber angles. So for the front, we're going to use the SLA double wishbone setup, which is basically A-arms on upper and lower, and on the SLA setup, it's called the short long arm suspension. The lower A-arm is longer than the upper A-arm, which reduces the camber changes when you go into cornering and stuff like that. So reducing the camber wear, or camber change, will reduce the amount of tire wear on the outside edges, and also keep your contact patch more flat and stable on the road. So the connection for the suspension to the sprung mass. So basically, right here we have the tubing of the chassis itself, and the connection is going to be at points that we're going to have to design for, and we might have to modify the chassis slightly to accommodate for it. Other than that, we can either implement the brackets into the chassis tubing itself, or attach brackets and weld them on afterwards. Connection to the unsprung mass, we can design basically a knuckle. So we can actually use the set points that we designed for, and we can machine one of these out of like a block of aluminum. It'll be lightweight, it'll still be strong enough to support all the forces it's going to bear. And it's also going to have to be designed to hold on to all the braking components, the wheel hub. It's going to have to mount the wheels and tires, and also any regenerative braking system that's going to go on there as well. This is an overview of basically the whole unsprung mass. You have the wheel hub, you have your hub bearings, your rotor, and usually a lot of cars have a backing plate, but we don't need one of those on these. And without the backing plate, you'll actually increase like the heat transfer away from the brakes and stuff like
good
that.
question. You're going to design all this yourself, or is there an off-the-shelf
I mean,
assembly you could use?
you can use like a standard hub bearing setup, and then design a spindle to fit that. That'll accommodate for our suspension design. I mean, the rotors we can purchase as well.
Right. I'm just wondering what the ME side is. How much are they expecting you to go into the details of all these components? You know.
Well, I mean, you can also, research and take what kind of spindle and stuff like that, what kind of hub bearings you want to use to reduce what kind of friction and all that.
I mean,
kind of
do you
stuff.
guys want them to design all this?
Usually the steering not going to be pre-designed, because then based on the suspension design, it's very hard to find something that will fit. But usually the drive shaft will sort of buy off the shelf, or not modify it, you can't manufacture that very easily.
Sure.
But a lot of this, the
Yeah.
great distance stuff, a lot of that is buy off the shelf.
Yeah, the drive shaft would go through actually all these components, and then would be connected here on the splines.
Right. I was just wondering if you have to design each and every one of these little components.
No, many of
Fit them all.
purchase.
I was gonna clear it up, if we're gonna actually buy the wheel hub, and that would have everything on it, and then the spindle we design, and we can attach the spindle to have any mounting points that we designed for, and as long as that fits to the wheel hub, we can buy the wheel hub and we'll have the.
Okay. Sounds a little more feasible.
Alright, my name is Tomas Blatchy, and I'm gonna talk about a push rod spring damper, so we're gonna have on the car. We're going to use the push rod to transfer the suspension forces from the wheels to the chassis. This reduces the amount of unsprung weight as the spring and shocks move inboard. So like when you have double A-arms, you put a shock, if you have the shock in between there, and like it sends the it pins up against the chassis. Here, I'll go back a couple slides. Basically, right here, this is still all part of unsprung weight because it's all moving up and down with the wheel. But if having the push rod design, which will be this, actually, we're gonna have a push rod design which looks like this, and the spring compression rate can be controlled, as I'll explain in the next slide, and it increases aerodynamics because it's open wheel applications. You don't have the spring sitting here; it moves inside the chassis. So basically, what will happen is the linkage is going to be set up so as the wheel travel increases, as this wheel is moving up and down, the push rod will make closer to a 90-degree angle with the piston. So what will happen is as it's deflecting, the efficiency of the spring is going to increase, so it'll stiffen up. So you're going to have it'll stiffen with wheel travel. So, and also a belt crank will allow you to place the springs horizontally. You can transform the up and down motion into like a horizontal motion using any linkage. And so this is just an example where you can put the shocks in different orientations. We have a test plan, and basically for the test plan, we're gonna first observe the geometry and like pick the mounting points from the chassis. It involves knowing some information about the chassis. We're gonna measure these and like input them into atoms, and like basically we're gonna build it in atoms and run simulations with our set geometry. Then we have to predict changes from our current setup to get better results in the simulations. So it's basically an iterative process looking to improve performance. So most of the modeling will be done fully on the computer, and once it's fully done on the computer, it will be implemented into the vehicle. Once it's built, we can fine-tune the spring stiffness and stuff, but the design itself and the geometry and the mounting points, that will all be determined with the Atom software. Suspension budget, you have the rod end, springs, shocks, wheel hub, the aluminum block to use to make the spindle, to attach to the wheel hub, so we can use any points that we want in our geometry. And a suspension timeline, basically, we're already starting the research. We'd like to have a preliminary design by the next milestone, which is on November 14th. We'd like to have a model built we'd like to have the model compiled, find the connections from the wheel hub spindle, just do the calc compile and the final product build. Risk assessment, there's some risk associated with our design and funding our design, and you have individual components